Hello everyone. Welcome to day 1. In this video, we will explore one of the most transformative technologies of our era. AI has redefined industries, reshaped economies, and permeated our daily lives in ways we couldn't have imagined a few decades ago. In this session, we'll break down what AI is, its evolution through significant milestones, and how it is applied in the real world. We'll also address its diverse forms, from narrow AI systems like virtual assistants to the theoretical concepts of general and super AI. By the end, you'll have a deeper appreciation of AI's capabilities, challenges, and the opportunities it presents for the future. Let's begin by setting the stage with foundational concepts. So, what exactly is artificial intelligence? At its core, AI involves creating systems that can perform tasks that typically require human intelligence. This includes problem solving, recognizing patterns, making decisions, and understanding language. For instance, when you use a voice assistant like Siri or Alexa, AI processes your voice, understands your intent, and responds accordingly. AI can be categorized into 3 broad types. 1. Narrow AI, which excels in specific tasks, like recommending movies or identifying objects in photos. 2. General AI, a theoretical system that could understand and perform any intellectual task a human can. This remains a goal for the future. 3. Super AI, a speculative concept where machines surpass human intelligence in all respects. Understanding these distinctions helps frame how we discuss AI's current capabilities and its potential trajectory. Let's delve deeper into the categories of AI, starting with narrow AI. Narrow AI systems are all around us and dominate today's applications. These systems are designed to perform specific tasks exceptionally well, such as analyzing medical scans, recommending products on e-commerce platforms, or powering autonomous cars. However, they cannot generalize beyond their predefined functions. Next, we have general AI, a concept often portrayed in science fiction. General AI would match human intelligence and versatility, enabling it to adapt to any task, whether it's learning a new language, solving complex problems, or reasoning about abstract concepts. While this remains hypothetical, it is a long-term goal for researchers. Finally, there's super AI, which transcends human intelligence. This idea sparks debates about ethical, societal, and philosophical implications, from ensuring safety to rethinking humanity's role in an AI-dominated future. The history of AI begins in the mid-20th century with foundational contributions from visionaries like Alan Turing. In 1950, Turing proposed the Turing test, a way to evaluate a machine's ability to exhibit intelligent behavior indistinguishable from that of a human. This marked the beginning of serious discussions about machine intelligence. By 1956, the Dartmouth Conference brought together pioneers who formally established AI as an academic discipline. Researchers initially focused on creating rule-based systems, where machines followed predefined instructions to solve problems. These systems excelled in specific areas, such as solving logical puzzles or performing basic calculations. However, they lacked adaptability, which limited their broader application. Despite these limitations, this era laid the groundwork for more advanced AI technologies by sparking curiosity and defining core challenges, like how to enable machines to learn and reason beyond fixed rules. AI's journey hasn't been a smooth ascent. During the 1970s and 1980s, the field experienced what's known as the AI winter. This period was marked by dwindling funding and skepticism about AI's potential, largely due to unmet expectations. Early systems had shown promise, but limited computational power and a lack of large datasets hindered progress. Many systems failed to scale or handle real-world complexities, leading to disillusionment among researchers, governments, and investors. However, the 1980s saw a revival with the advent of expert systems. These rule-based programs mimicked decision-making processes in specific domains, such as medical diagnosis and financial analysis. While not without limitations, expert systems rekindled interest and demonstrated AI's potential to solve specialized problems effectively. This period taught researchers valuable lessons about realistic goal setting and the need for better technology and data. The late 20th century marked a transformative shift in AI from rigid, rule-based systems to dynamic, data-driven approaches. This era gave rise to machine learning, where algorithms began to learn patterns and make decisions based on data rather than pre-programmed rules. Pioneering techniques like decision trees and early neural networks laid the foundation for modern AI. One of the most notable milestones during this period was in 1997 when IBM's Deep Blue defeated reigning chess champion Garry Kasparov. This event demonstrated that data-driven approaches, combined with immense computational power, could outperform human expertise in highly strategic tasks. It was a pivotal moment, showcasing the practical potential of AI and solidifying its place as a force to be reckoned with. This era also paved the way for the deep learning revolution that would follow in the next decade. Deep learning marked a revolutionary phase in AI's development. In 2006, Geoffrey Hinton and his collaborators popularized the concept of deep neural networks and the backpropagation algorithm, enabling machines to learn intricate patterns in large datasets. This breakthrough paved the way for significant advancements in AI. A watershed moment came in 2012 with AlexNet's victory in the ImageNet competition, a benchmark challenge in image recognition. AlexNet demonstrated the incredible potential of deep neural networks to achieve human-like performance in complex tasks. This success propelled AI into new domains, including natural language processing, speech recognition, and autonomous systems. Today, deep learning powers applications ranging from facial recognition and language translation to self-driving cars and medical imaging, proving its versatility and transformative power. Artificial intelligence has seamlessly integrated into our everyday lives, thanks to advances in powerful models like GPT and BERT. These models have revolutionized natural language processing, enabling AI to generate human-like text, translate languages, and provide conversational assistance. In healthcare, AI supports diagnostics and treatment planning, while in finance, it detects fraud and optimizes trading strategies. Transportation has been transformed with autonomous vehicles and intelligent traffic systems. Entertainment platforms like Netflix and Spotify use AI to recommend content tailored to individual preferences. From virtual assistants like Alexa and Siri to smart home systems, AI has become an indispensable part of our daily routines. Its ubiquity highlights not just its potential, but also its importance in shaping the future of society. The versatility of AI is evident in its real-world applications across diverse industries. In healthcare, AI systems analyze medical images, accelerate drug discovery, and create personalized treatment plans based on patient data. In finance, AI detects fraudulent activities in real time and drives algorithmic trading by analyzing vast amounts of market data. The transportation sector benefits from AI-powered autonomous vehicles and intelligent traffic management systems, reducing congestion and enhancing safety. In retail, recommendation systems provide personalized shopping experiences, while predictive analytics optimize inventory management. These applications demonstrate AI's potential to revolutionize processes, improve efficiency, and create value across the board. AI's journey has been marked by pivotal milestones that highlight its progress and potential. In 1950, Alan Turing's Turing test laid the conceptual groundwork for evaluating machine intelligence. The Dartmouth Conference in 1956 officially established AI as a field of study. In 1997, IBM's Deep Blue defeated chess champion Garry Kasparov, proving that machines could excel in strategic reasoning. The 2012 success of AlexNet in the ImageNet competition marked the dawn of the deep learning revolution, setting new benchmarks in computer vision. In recent years, groundbreaking models like GPT-3 and AlphaGo have pushed the boundaries of natural language processing and strategic problem solving, further showcasing the transformative power of AI. To understand how AI works, we must examine its core mechanisms. AI is built on three foundational approaches: machine learning, deep learning, and reinforcement learning. Machine learning involves training algorithms on datasets to identify patterns and make predictions. Deep learning, a subset of machine learning, utilizes neural networks with multiple layers to process complex information, such as images or natural language. Reinforcement learning focuses on decision-making, where algorithms learn by interacting with an environment and receiving feedback in the form of rewards or penalties. Data is the lifeblood of AI. Algorithms process vast amounts of data to uncover patterns and relationships. For instance, AI can analyze customer behavior to predict product preferences or study satellite images to track climate changes. Behind the scenes, powerful infrastructure supports AI's capabilities. GPUs, graphics processing units, and TPUs, tensor processing units, enable efficient processing of large datasets, while cloud platforms provide the scalability needed for AI. These components together form the backbone of AI systems. While AI offers tremendous benefits, it also presents significant challenges. One critical issue is bias. Since AI systems learn from data, they can inadvertently replicate and amplify societal biases present in their training datasets. Ethical considerations also come into play. How do we ensure AI is used responsibly? Questions around privacy, accountability, and fairness require thoughtful deliberation. Additionally, the energy consumption of large-scale AI models, such as GPT-3, raises environmental concerns. Training and deploying these models demands substantial computational resources, contributing to carbon emissions. Security is another concern. AI systems can be vulnerable to adversarial attacks, where malicious inputs are designed to deceive the model. Ensuring robustness against such attacks is crucial, especially in sensitive applications like healthcare or defense. Data is the foundation upon which AI systems are built. AI systems rely heavily on two main types of data, structured and unstructured. Structured data includes organized formats like databases and spreadsheets, while unstructured data includes formats like text, images, and videos. For example, datasets like ImageNet have been instrumental in advancing computer vision, providing millions of labeled images for training deep learning models. Similarly, Common Crawl, a repository of web data, has been vital for training NLP models like GPT. The quality of data is just as important. Inaccurate, biased, or incomplete data can lead to flawed AI systems, emphasizing the need for robust data collection and pre-processing pipelines. Properly leveraging data allows AI to unlock its full potential across various applications. As AI becomes more integrated into society, ethical considerations become increasingly critical. One key issue is accountability, determining who is responsible when AI systems make decisions that have significant consequences. For example, in the case of autonomous vehicles, if an accident occurs, is the manufacturer, software developer, or user accountable? Transparency is another essential aspect. Many AI systems, especially deep learning models, are often considered black boxes where their internal decision-making processes are not easily understood. Ensuring these systems are explainable helps build trust and allows stakeholders to understand how and why decisions are made. Equity is also paramount. AI systems must be designed to avoid discrimination and promote fairness, especially in sensitive areas like hiring, lending, or law enforcement. Finally, regulation plays a crucial role. Governments and organizations must develop comprehensive guidelines and laws to govern AI use, balancing innovation with public safety and ethical responsibility. The future of AI is filled with exciting possibilities and significant challenges. Emerging trends like explainable AI aim to make AI systems more transparent and interpretable, addressing the black box problem. Federated learning offers new ways to train AI models on decentralized data, improving privacy without sacrificing performance. AI presents vast opportunities. In personalized medicine, AI could tailor treatments to individual genetic profiles, enhancing efficacy and reducing side effects. Climate modeling powered by AI can help predict and mitigate the impacts of climate change. In education, AI-driven tools can provide customized learning experiences, bridging gaps in access and quality. However, challenges persist. Aligning AI development with human values is essential to ensure it benefits society as a whole. Collaboration across nations, industries, and disciplines will be crucial to address ethical, technical, and regulatory concerns. Machine learning, ML, is a core branch of artificial intelligence, AI. AI is the broader field focused on creating systems that simulate human-like intelligence. While AI encompasses various methods like rule-based systems or expert systems, machine learning is one of the most influential and widely used techniques within AI. Instead of writing exact step-by-step instructions for the machine to follow, we allow the machine to analyze and learn patterns from data. A classic example of this is spam filtering in emails. Rather than defining a list of words that indicate spam, a machine learning model learns from thousands of labeled examples, spam versus non-spam, and begins to identify the characteristics that differentiate the two. The more data the system is exposed to, the better it gets at making predictions. The relationship between artificial intelligence and machine learning can be seen as a hierarchy, where machine learning is a specialized technique within the larger framework of AI. AI is about building intelligent systems that can perform tasks that traditionally required human-like cognition, such as recognizing speech, making decisions, or translating languages. Machine learning, on the other hand, is a more specific technique that allows systems to learn from experience and data. It's often referred to as a subset of AI because it is one of the most powerful and widely used approaches to achieving intelligent behavior in machines. What makes ML particularly important is its ability to improve over time as it is exposed to more data. For example, in speech recognition applications like Siri or Alexa, the system gets better at understanding your voice the more it interacts with it, thanks to machine learning algorithms. Machine learning can be divided into three primary types. Supervised learning. This is the most common type of machine learning. It uses labeled data, where each input example is paired with a correct output. The model is trained on this labeled data to learn the relationship between the inputs and the outputs. After training, the model can predict the output for new, unseen data. A classic example is image classification, where the algorithm is trained on thousands of labeled images, e.g., pictures of cats and dogs, and learns to classify new images as either a cat or a dog based on the learned features. Unsupervised learning. In unsupervised learning, the algorithm is given unlabeled data. There are no predefined labels, so the algorithm tries to identify patterns or structures on its own. A common application of unsupervised learning is clustering, where the algorithm groups data points based on similarity. Reinforcement learning. This is a unique type of learning in which an agent learns to interact with an environment by performing actions and receiving feedback. The feedback, in the form of rewards or punishments, helps the agent improve its behavior over time. This type of learning is widely used in areas such as robotics and game AI, like AlphaGo or chess playing AI. Supervised learning is the most commonly used type of machine learning. It is called supervised because the model is trained on labeled data, where each data point is paired with the correct output. The machine's job is to learn the relationship between the input data and its corresponding label. Once trained, the model can then make predictions on new, unseen data. For example, in image recognition, we might train a model on a dataset of images labeled with the correct categories, e.g., cat, dog. The algorithm learns to identify distinguishing features like the shape of ears or the size of the body, and it can then use this knowledge to classify new images. Supervised learning is also widely used in medical diagnoses. For instance, a model might be trained with historical data, such as patient symptoms, medical history, and lab results, to predict whether a new patient has a particular disease. The key advantage of supervised learning is that, because we know the correct answers, labels, during training, we can directly measure how well the model performs by comparing its predictions to the actual outcomes. Unsupervised learning differs from supervised learning in that the model is given unlabeled data. There are no predefined labels or outcomes for the model to learn from. Instead, the goal of unsupervised learning is to identify underlying patterns, structures, or relationships in the data. This can involve grouping similar data points together, clustering, or identifying outliers, anomaly detection. A common example of unsupervised learning is market basket analysis, where an algorithm looks for associations between products that are frequently bought together. For example, it may find that customers who buy milk are also likely to buy bread, which can then inform targeted marketing campaigns. Another key application of unsupervised learning is clustering. For instance, clustering algorithms like k-means group customers into segments based on purchasing behavior, demographics, or other characteristics. This segmentation can help businesses target specific customer groups with personalized offers. Reinforcement learning, RL, is a type of machine learning where an agent interacts with an environment and learns through trial and error. The agent performs actions within the environment and receives feedback in the form of rewards or punishments based on its actions. Over time, the agent learns to optimize its strategy to maximize the cumulative reward. In game-playing AI, RL has been used to train agents to play complex games like Go and chess. One of the most famous examples of RL is AlphaGo, the AI developed by DeepMind, which used RL to master the game of Go. The agent played millions of games, gradually learning strategies that human experts couldn't even identify. Another common use case for RL is in self-driving cars, where the car learns to navigate traffic by interacting with its environment. The car receives feedback, positive or negative, based on its actions, such as stopping at red lights, avoiding obstacles, or taking the correct turns. RL enables systems to continuously learn and improve from experience. Building a machine learning model is a multi-step process that involves several stages. First is data collection. The success of any ML model depends heavily on the quality and quantity of data used to train it. The data must be relevant to the problem at hand and collected in a way that represents the real-world scenario the model will encounter. Once the data is collected, it needs to be pre-processed. Pre-processing tasks include cleaning the data, removing duplicates, handling missing values, normalizing features, scaling numerical values, and encoding categorical data, converting labels to numerical values. This step ensures that the data is in a suitable format for the ML algorithms. Next comes model selection. Depending on the problem, e.g., classification, regression, clustering, we choose an appropriate machine learning algorithm. This could be something simple like linear regression or more complex like neural networks. Once the model is selected, training begins, where the model learns from the data and adjusts its parameters. Finally, after training, the model needs to be evaluated using test data that it hasn't seen before. If the model performs well, it can be deployed to make predictions or automate processes in the real world. In machine learning, data is everything. The success of any model is directly tied to the quality of the data it is trained on. This is why the first step in any ML project is often focused on data collection. The data must be relevant, diverse, and representative of the problem you're trying to solve. Once the data is collected, it often needs to be pre-processed. Data cleaning involves handling missing values, removing outliers, and ensuring that the data is consistent. Structured data is highly organized and fits neatly into rows and columns, such as in a relational database or a spreadsheet. Unstructured data, on the other hand, includes text, images, audio, and video, which require more complex processing techniques, such as natural language processing, NLP, for text or deep learning models for images. When building a machine learning model, it's essential to split the data into at least 3 subsets: training data, testing data, and validation data. Training data is used to teach the model how to make predictions. The model learns patterns and relationships from this data to optimize its parameters. Testing data is kept separate from the training data. After the model is trained, it's tested on this data to evaluate its performance. Testing data gives a measure of how well the model can generalize to new, unseen data. Validation data is used for fine-tuning the model's hyperparameters. Hyperparameters are the settings that control the learning process. By using validation data, we can adjust these hyperparameters to improve the model's performance. By splitting the data into these 3 sets, we ensure that the model can learn from the training data, be evaluated using testing data, and optimized for better results using validation data. In machine learning, one of the biggest challenges is achieving the right balance between overfitting and underfitting. Both issues can significantly impact the performance of a model, so understanding them is crucial. Overfitting occurs when the model becomes too complex and essentially memorizes the training data. The model learns to fit not just the true patterns in the data, but also the noise. When this happens, the model performs exceptionally well on the training data, but fails to generalize to new, unseen data. Underfitting, on the other hand, happens when the model is too simple to capture the underlying patterns in the data. It doesn't learn enough from the training data, resulting in poor performance both on the training data and on new data. For instance, a linear regression model might struggle to fit nonlinear data, leading to underfitting. The key goal is to find the right balance, a model that is complex enough to capture the essential patterns in the data, but simple enough to avoid overfitting. This balance is typically achieved through cross-validation and techniques like regularization. The bias-variance trade-off is a fundamental concept in machine learning. It explains the relationship between a model's complexity and its ability to generalize to new data. Bias is the error introduced by overly simplistic model assumptions. A high-bias model makes strong assumptions about the data, like assuming a linear relationship when the data is actually more complex. This can lead to underfitting, where the model fails to capture the underlying structure of the data. Variance, on the other hand, measures how sensitive the model is to fluctuations in the training data. A high-variance model is very flexible and can adapt to small changes in the data, but this flexibility can result in overfitting, where the model learns not just the underlying patterns, but also the noise in the training data. The challenge is to find the right model complexity that minimizes both bias and variance. A simple model may have high bias but low variance, while a complex model may have low bias but high variance. Regularization techniques can help manage this trade-off by penalizing overly complex models, thus preventing overfitting while maintaining enough flexibility to learn from the data. After training a machine learning model, it's critical to evaluate its performance. While accuracy is a simple and commonly used metric, it doesn't always give us the full picture, especially when dealing with imbalanced datasets. In situations where one class is more frequent than the other, a model could be highly accurate by simply predicting the majority class, but this would not be useful. This is where precision, recall, and F1 score come in. Accuracy is the percentage of correct predictions out of all predictions made by the model. It's a straightforward metric, but can be misleading in cases where the classes are imbalanced. Precision measures how many of the instances predicted as positive are actually positive. For example, in spam detection, precision answers the question, of all the emails flagged as spam, how many were truly spam? Recall, or sensitivity, measures how many actual positives were correctly identified by the model. In the context of spam detection, recall answers, of all the spam emails, how many were correctly flagged? The F1 score is the harmonic mean of precision and recall, providing a balanced measure that takes both metrics into account. Finally, the confusion matrix is a tool that visualizes these metrics and helps to understand the performance of a classification model by showing the counts of true positives, true negatives, and false negatives. This allows for a deeper insight into how well the model is performing, especially when the class distribution is skewed. There are several widely used machine learning algorithms, each with its strengths and best use scenarios. Here are a few common ones. Linear regression. This is one of the simplest and most commonly used algorithms for regression tasks, where the goal is to predict a continuous value. It assumes a linear relationship between the independent variables, features, and the dependent variable, target. For example, linear regression can be used to predict housing prices based on features like size, location, and number of rooms. Despite its simplicity, linear regression is powerful and often serves as a baseline model for comparison with more complex algorithms. Decision trees. Decision trees are a popular choice for both classification and regression tasks. They work by splitting the data into branches based on feature values and making decisions at each node based on certain thresholds. The model is built by recursively splitting the data in ways that best separate the data into distinct classes or values. Decision trees are easy to interpret, making them useful in scenarios where model transparency is important. K-nearest neighbors, KNN, is a lazy learning algorithm, meaning it doesn't learn a model explicitly. Instead, it stores all the training data and makes predictions based on the closest K data points to the query instance. It's simple, intuitive, and often used for classification tasks. For example, it can be used to classify an unknown animal based on features like size, shape, and color by comparing it to known animals in the dataset. However, KNN can become computationally expensive as the dataset grows. As we move forward, we will dive deeper into specific algorithms and techniques, such as neural networks, support vector machines, SVM, and ensemble methods like random forests. Additionally, we will explore real-world applications of machine learning in fields such as healthcare, finance, and autonomous systems. By gaining hands-on experience with ML libraries like scikit-learn and TensorFlow, you will be able to apply these concepts to solve real-world problems and make informed decisions based on data. The journey to mastering machine learning is ongoing, but by starting with these foundational principles, you'll be well equipped to continue learning and applying ML in various domains. Keep practicing, experimenting with new algorithms, and working on real-world datasets to refine your skills. Neural networks are a core component of machine learning, inspired by the biological neural networks found in the human brain. Just like the brain processes information through neurons and synapses, a neural network processes input data through artificial neurons and layers. These networks are trained to identify patterns, relationships, and structures within the data. Neural networks are incredibly versatile, and they can be used for a variety of tasks including image classification, predictive analysis, speech recognition, and natural language processing. The most important feature of neural networks is their ability to learn from the data through training, where the model adjusts its parameters to minimize errors. By learning from examples, neural networks are able to make predictions on new, unseen data. The idea behind neural networks is based on a structure of the human brain, which is made up of billions of neurons that are interconnected by synapses. Each neuron receives signals from other neurons, processes them, and then passes on a signal to other neurons. Artificial neural networks, ANNs, are a simplified version of this biological process. In a neural network, artificial neurons, also called nodes or units, are connected through layers, much like how biological neurons are connected by synapses. Each artificial neuron takes an input, processes it with a mathematical function, and produces an output, which becomes the input for other neurons. The strength of the connection between neurons is represented by weights, which are adjusted during the training process to improve the accuracy of the model. This biological inspiration allows neural networks to learn patterns and make decisions in ways similar to how our brains function, but at a much faster and more scalable level. At the core of every neural network are its neurons, which are the computational units that receive and process data. A typical neural network consists of multiple layers: the input layer, one or more hidden layers, and the output layer. Each layer consists of neurons where the input layer receives the initial data, such as images, text, or numerical data. The hidden layers perform complex transformations on the input data using weights and biases to uncover hidden patterns. The output layer provides the final prediction or classification based on the learned information. In addition to neurons and layers, weights and biases are critical components of the network. Weights determine the strength of the connection between neurons, while biases help adjust the output of a neuron. During the training process, the weights and biases are updated using algorithms like gradient descent to minimize errors and improve predictions. Together, these components form the building blocks that allow a neural network to learn and make decisions. An important feature of neural networks is the activation function, which adds nonlinearity to the network. Without nonlinearity, the neural network would essentially be limited to performing linear transformations, which would make it unsuitable for complex tasks like image recognition or natural language processing. The activation function determines whether a neuron should be activated and how it should transform the input it receives. There are several common activation functions. Sigmoid outputs a value between 0 and 1, often used in binary classification tasks. ReLU rectified linear unit outputs the input directly if it's positive and 0 if it's negative, commonly used in hidden layers due to its simplicity and efficiency. TAN, similar to sigmoid but outputs values between -1 and 1, making it more suitable for some tasks compared to sigmoid. Each activation function has its own characteristics and is chosen based on the specific task at hand. The key role of the activation function is to introduce the necessary nonlinearities to the neural network, allowing it to model complex relationships in the data. Forward propagation is the process of passing the input data through the network to generate a prediction. The input data is fed into the input layer, and it is passed layer by layer through the hidden layers. At each neuron, the data is processed by multiplying the input with the weights and adding the bias. The result is then passed through the activation function, which determines whether the neuron should be activated and how much influence it should have on the next layer. This process continues until the data reaches the output layer, where the final prediction or classification is made. For example, in a binary classification task, the output layer might use a sigmoid activation function to produce a probability value between 0 and 1, representing the likelihood of the input belonging to a particular class. The goal of forward propagation is to make the model's output as close as possible to the correct label, which will be adjusted during the backpropagation step. After the forward propagation process, the model calculates the error or loss by comparing its output to the actual label. This error is then propagated backward through the network in a process called backpropagation. Backpropagation helps adjust the model's weights and biases to minimize the error, improving the network's performance over time. Backpropagation works by calculating the gradient of the loss function with respect to each weight. This gradient indicates the direction in which the weights should be adjusted to reduce the error. The adjustment process is done using an optimization algorithm like gradient descent. Gradient descent updates the weights iteratively by moving in the direction of the negative gradient to reduce the error. This process is repeated over multiple iterations or epochs until the model converges to a solution that minimizes the error. Gradient descent is the optimization technique used to minimize the loss function in neural networks. The goal of training a neural network is to find the optimal weights and biases that result in the smallest possible error. Gradient descent helps achieve this by adjusting the weights iteratively based on the gradients of the loss function with respect to the parameters. There are 3 common types of gradient descent. Batch gradient descent uses the entire dataset to compute the gradient and update weights. While it's computationally expensive, it ensures stable convergence. Stochastic gradient descent, SGD updates weights after processing each training example. It's faster than batch gradient descent, but more noisy, leading to faster convergence, but potentially less stable. Mini-batch gradient descent, a compromise between batch and stochastic gradient descent, processing small batches of data at a time. It combines the benefits of both and is widely used in practice. Overfitting is a common problem in neural networks where the model becomes too complex and starts to memorize the training data, including noise and irrelevant details. This results in poor generalization, meaning the model performs well on the training data but fails to make accurate predictions on new, unseen data. The goal is to generalize well, so the model can perform accurately across various scenarios. Regularization techniques help prevent overfitting by imposing penalties on large weights or reducing the complexity of the model. Common regularization methods include L2 regularization. Ridge adds a penalty term to the loss function that is proportional to the square of the weights. L1 regularization. Lasso adds a penalty term proportional to the absolute value of the weights, encouraging sparsity in the model. Dropout. Randomly drops some neurons during training, forcing the network to learn more robust features and preventing it from relying too heavily on any single neuron. There are several types of neural networks, each designed to handle different kinds of data and tasks. The most basic type is the feed-forward neural network, FNN, which consists of an input layer, hidden layers, and an output layer. The data moves in one direction from input to output, with no cycles or loops. More specialized neural networks include convolutional neural networks, CNNs, commonly used in image and video recognition. CNNs use convolutional layers to scan local features in the data and build hierarchical representations of the data. CNNs are highly effective for tasks like image classification and object detection. Recurrent neural networks, RNNs, which are designed for sequential data. RNNs have loops that allow information to persist from one time step to the next, making them ideal for tasks like speech recognition, text generation, and time series prediction. Training a neural network involves feeding labeled data into the network, allowing it to make predictions, and then comparing those predictions to the actual labels to compute the loss. The network then updates its weights and biases using backpropagation and gradient descent, iterating through the dataset multiple times, epochs, to minimize the loss. Each epoch involves forward propagation and backpropagation to adjust the network's parameters. The process continues until the model's performance stabilizes, and further iterations no longer lead to significant improvement. Neural networks can take a long time to train, especially when working with large datasets, so computational resources and optimization techniques like batch processing or mini-batch gradient descent are often used to speed up training. After training a neural network, it's crucial to evaluate its performance. The most common evaluation metric is accuracy, which measures how often the model's predictions are correct. However, other metrics like precision, recall, and F1 score might be more appropriate depending on the specific task, especially in cases of imbalanced classes. The loss function also provides a way to evaluate the model's error. For classification tasks, cross-entropy loss is typically used, while for regression tasks, mean squared error, MSE, might be more appropriate. To prevent overfitting, it's essential to evaluate the model's performance on validation data, which was not used during training. Additionally, test data should be used to assess the model's generalization ability to new, unseen data. There are several powerful libraries available for building and training neural networks. TensorFlow and Keras, which is built on top of TensorFlow, are widely used in industry and academia. PyTorch is another popular framework, particularly favored for research due to its dynamic computation graph. These libraries allow you to easily build complex neural network architectures, train them on large datasets, and deploy them for real-world applications. Neural networks are used in many domains to solve complex problems. For instance, image recognition tasks like classifying images into categories, e.g., cat or dog, are powered by convolutional neural networks, CNNs, while recurrent neural networks, RNNs, are used in speech-to-text systems and language translation tasks. While neural networks are powerful, they come with challenges. First, they require large amounts of labeled data to train effectively. This can be a major barrier in fields where collecting large datasets is difficult or expensive. Second, training neural networks is computationally expensive. Deep networks with millions of parameters can require significant computational power, often needing GPUs or distributed computing systems. As a result, Neural networks can be slow to train, especially with complex models and large datasets. Finally, overfitting remains a significant challenge, especially when there's not enough data. Regularization techniques like dropout and early stopping are critical for addressing this issue and ensuring the model can generalize well to new data. Neural networks are used in a wide range of applications. Some of the most popular use cases include image recognition. Convolutional neural networks, CNNs, are the gold standard in image classification and object detection tasks. For example, they are used in facial recognition systems, medical image analysis, and autonomous vehicles to identify objects in the environment. Natural language processing, NLP recurrent neural networks, RNNs, and more advanced models like transformers are used in tasks such as text generation, speech recognition, and machine translation. Models like GPT-3 and BERT use deep learning to process and understand human language in applications like chatbots, sentiment analysis, and language translation. Time series forecasting. Neural networks are also powerful for predicting future values in time series data, such as stock prices, weather forecasting, and sales prediction. RNNs and their variations, such as long short-term memory, LSTM, networks, excel in these tasks because of their ability to learn temporal dependencies in data. Looking ahead, several exciting developments are shaping the future of neural networks. One of the most significant advancements is the rise of transformer models, which have revolutionized NLP tasks. Models like BERT, GPT, and T5 have set new benchmarks in machine translation, text generation, and question answering. Beyond NLP, transformer-based architectures are also making their way into other domains, such as computer vision, where vision transformers, VIT, are showing promising results in image classification tasks. The flexibility and scalability of transformers have opened up new possibilities, and we can expect even more breakthroughs in the coming years. Another major trend is the development of multimodal neural networks, which are capable of processing and learning from multiple types of data, such as combining text, images, and audio. These networks are poised to power next-generation AI systems that can understand and generate complex content across different media. Lastly, while neural networks are incredibly powerful, they tend to be computationally expensive. As we look to deploy these models on a larger scale, there's a growing focus on developing efficient neural networks that can achieve similar performance with less computational cost. Techniques like model pruning, quantization, and knowledge distillation are being explored to make models smaller, faster, and more energy efficient, which is particularly important for mobile and edge devices. Deep learning is a subfield of machine learning that focuses on using neural networks with multiple layers to automatically learn from vast amounts of data. Unlike traditional machine learning models, which require manual feature engineering, deep learning models are designed to automatically learn feature representations from raw data. This makes deep learning particularly powerful for tasks like image recognition, speech processing, and natural language understanding. The capability of deep learning to learn complex patterns directly from raw data without the need for human intervention in feature extraction has led to breakthroughs in fields like computer vision, speech recognition, and game-playing AI. At its core, deep learning is an advanced form of machine learning that utilizes multi-layered artificial neural networks. The main idea is that these networks can automatically learn hierarchical feature representations from raw input data. Traditional machine learning algorithms require handcrafted features to be inputted into the model. Deep learning models typically consist of an input layer, several hidden layers, and an output layer. During training, the model adjusts the weights of the connections between neurons in the hidden layers through backpropagation, a technique that adjusts weights to minimize the error between the predicted and actual outputs. One of the key advantages of deep learning is its ability to handle very large datasets and automatically extract meaningful features, which is crucial for applications such as image recognition and speech-to-text systems. As a reminder, the architecture of a neural network consists of three primary components: the input layer, the hidden layers, and the output layer. The input layer takes the raw data, which can be anything from images to text, and passes it to the subsequent hidden layers. Each hidden layer performs complex transformations on the data by applying mathematical operations, followed by an activation function to introduce nonlinearity, enabling the network to learn from complex patterns. The neurons in each layer are connected by weights that determine the strength of the signal transmitted between layers. These weights are adjusted during training, allowing the network to learn relationships in the data. The strength of these connections is updated through backpropagation, which helps the model minimize the error in predictions. Activation functions like ReLU, sigmoid, or TAN are applied at each neuron to decide whether it should activate and pass the signal forward to the next layer. Without these nonlinear activation functions, the network would only be able to learn linear relationships, limiting its capacity to model complex patterns. The deep layers, stacked on top of each other, allow the model to learn increasingly abstract representations of the input data. In a deep learning model, the process begins with a forward pass. The input data is fed into the input layer and passed through each hidden layer, where mathematical transformations are applied. At each layer, the data is processed by multiplying it by weights and adding biases. The result is passed through an activation function, which determines if the neuron should fire or pass the signal forward. During training, the initial weights are set randomly. The model then performs a forward pass to generate predictions. These predictions are compared to the actual outputs, and the error, or loss, is calculated using a loss function. The most common loss function is mean squared error for regression tasks or cross-entropy loss for classification tasks. To improve the model, backpropagation is used. Backpropagation calculates the gradient of the loss function with respect to each weight in the network. Using this information, the weights are updated through an optimization algorithm like gradient descent. The goal of training is to minimize the error by adjusting the weights iteratively, which is done through multiple epochs until the model converges to a solution. Neural networks come in several different architectures, each designed for specific types of data and problems. Let's revisit the three common types. Feed-forward neural networks, FNN. This is the most basic type of neural network, where data flows in one direction, from the input layer through the hidden layers to the output layer. There are no loops or cycles in the network, and it's generally used for simple tasks like classification or regression. Convolutional neural networks, CNNs, are specialized networks primarily used for image processing and computer vision tasks. They include convolutional layers that apply filters to input data to capture spatial hierarchies, such as detecting textures and shapes in images. CNNs are the backbone of most modern image classification models. Recurrent neural networks, RNNs, are designed for processing sequential data like time series, text, or speech. Unlike feed-forward networks, RNNs have loops that allow information to persist from one time step to the next. This makes them ideal for tasks where context from previous inputs is important, such as language modeling or speech-to-text systems. Convolutional neural networks, CNNs, have revolutionized the field of computer vision. These networks are particularly well-suited for tasks like image classification, object detection, and image segmentation. CNNs work by applying convolutional filters, also called kernels, that slide over the input data to detect local patterns such as edges, textures, or shapes. These filters capture spatial hierarchies in the data, which allows the network to learn both low-level and high-level features. In addition to convolutional layers, CNNs also use pooling layers to reduce the spatial dimensions of the data, focusing on the most important features and making the network more computationally efficient. Max pooling is the most common pooling technique, which selects the maximum value in a small region of the image. Pooling reduces the amount of data the network needs to process, while also making the model more invariant to small translations in the input image. The combination of convolutional and pooling layers allows CNNs to effectively capture complex features in images, making them the go-to architecture for computer vision tasks. Recurrent neural networks, RNNs, are designed to handle sequential data where the order of the inputs matters. Unlike feed-forward networks, RNNs have loops within their architecture, allowing information to persist from one time step to the next. This memory is key for tasks like speech recognition, language translation, and time series prediction, where the context from previous steps is important for understanding the current input. At each time step, an RNN takes the input and the previous hidden state to generate the current output. The output is then passed to the next time step as part of the hidden state. This allows the network to learn dependencies between inputs at different time steps. However, basic RNNs can struggle to capture long-range dependencies due to issues like the vanishing gradient problem, where gradients become too small to propagate through the network. To address this, more advanced architectures like long short-term memory, LSTM, networks and gated recurrent units, GRUs, were developed, which better capture long-range dependencies. Training a deep learning model involves a series of steps where the network gradually improves its performance on the task. It begins with the forward propagation, where the input data is passed through the network's layers to generate a prediction. The prediction is then compared to the actual output, and the error is computed using a loss function. The loss function quantifies how far the model's predictions are from the true labels, and a common loss function for classification tasks is cross-entropy loss. Once the loss is calculated, the next step is backpropagation, where the error is propagated backward through the network to update the weights. The gradient of the loss function with respect to each weight is calculated, and the weights are updated using an optimization algorithm, such as gradient descent. This process is repeated iteratively over multiple epochs, allowing the model to refine its parameters and minimize the loss. Over time, the model's performance improves as it learns to make more accurate predictions. In addition to the weights and biases learned during training, neural networks also have hyperparameters, which are settings that are defined before training begins. These hyperparameters play a significant role in determining the success of a model and include parameters such as learning rate, determines how large the weight updates will be during training. A learning rate that's too high can lead to overshooting the optimal solution, while a rate that's too low can result in slow convergence. Batch size defines the number of training samples used in one iteration of training. A smaller batch size provides a more accurate estimate of the gradient, while a larger batch size makes the training process more efficient. Number of layers refers to the depth of the network. Deeper networks can learn more complex features, but also require more data and computational resources. Tuning these hyperparameters is essential for building an effective deep learning model. Techniques like grid search, random search, and Bayesian optimization are commonly used to find the optimal combination of hyperparameters for a given problem. Overfitting happens when a model learns not only the underlying patterns in the training data, but also the noise, irrelevant fluctuations that do not generalize to new, unseen data. To combat overfitting, we use regularization techniques. L1 regularization, lasso, adds a penalty to the absolute values of weights, which can drive some weights to zero, effectively performing feature selection and preventing overfitting. L2 regularization, ridge, adds a penalty to the squared values of the weights, discouraging large weights and helping improve generalization. Dropout is a technique where random neurons are dropped during training, forcing the network to learn more robust features and reducing its dependence on any single neuron. By incorporating regularization techniques, deep learning models are less likely to overfit and can generalize better to new data. Transfer learning allows us to take a model trained on one task and adapt it to a different, but related, task. This approach is especially useful when there's limited labeled data for the new task. Instead of training a model from scratch, which requires a large dataset and significant computational resources, transfer learning leverages the knowledge the model has already learned from a different task. For example, a CNN trained on millions of images for image classification can be adapted to a new task like medical image analysis by fine-tuning its weights on a smaller dataset. Transfer learning drastically reduces the amount of data and training time needed for new tasks, making it an invaluable tool in many deep learning applications. Deep learning has had a transformative impact across various industries, particularly in fields that require understanding complex data. In computer vision, CNNs are widely used for image classification, object detection, and image segmentation. For example, deep learning models are used in autonomous vehicles to identify pedestrians, traffic signs, and other vehicles. In natural language processing, NLP, deep learning models, particularly RNNs and transformers, power tasks like sentiment analysis, machine translation, and speech recognition. Models like BERT and GPT-3 are capable of understanding and generating human-like text, enabling chatbots, language translation services, and automated content generation. Deep learning is also used in autonomous systems like self-driving cars and drones. These systems rely on deep learning to process data from sensors, cameras, and radars, allowing them to navigate, recognize objects, and make decisions in real time. The future of deep learning looks incredibly promising as we continue to see advancements in both neural network architectures and the applications of deep learning. One major area of progress is the integration of multimodal data, where models learn from diverse sources of information, such as text, images, and audio. This would enable AI systems to understand and generate complex multimodal content, improving tasks like video captioning and cross-modal search. Another important area is improving the efficiency and scalability of deep learning models. While deep learning has achieved impressive results, the computational power required to train these models can be enormous. Researchers are focused on developing techniques to make deep learning more efficient, such as model compression and knowledge distillation, which allow large models to be condensed into smaller, faster models without sacrificing performance. Energy efficiency is also becoming a key concern as AI models grow more complex. Despite its success, deep learning presents several challenges. First, it requires large amounts of labeled data to train models effectively. This can be a significant barrier in fields where labeled data is scarce or expensive to obtain. While techniques like transfer learning can mitigate this challenge, deep learning models still perform best with large datasets. Second, training deep learning models is computationally expensive. These models often require powerful hardware, such as GPUs or TPUs, to handle the vast amounts of data and complex computations. Lastly, deep learning models are prone to overfitting, especially when there is insufficient data. Overfitting occurs when the model becomes too complex and learns the noise in the data rather than generalizable patterns. Regularization techniques, like dropout and L2 regularization, help address this issue. Deep learning continues to evolve rapidly, with researchers pushing the boundaries of what these models can achieve. One of the most groundbreaking advancements has been the application of transformer architectures beyond NLP. Originally designed for tasks like machine translation and text generation, e.g., GPT, BERT, transformers have now expanded to areas like computer vision through models like vision transformers, VIT. These architectures are enabling more efficient and accurate processing of images and videos, while multimodal transformers are being developed to process and integrate data from multiple modalities. Another exciting development is neural architecture search, NAS, a technique that automates the design of deep learning architectures. Instead of manually deciding on the number of layers, neurons, or activation functions, NAS uses optimization algorithms to discover the best performing architectures for a given task, significantly reducing the time and expertise needed for model development. Lastly, federated learning is addressing one of the biggest challenges in AI, data privacy. In federated learning, models are trained directly on users' devices, and only the model updates are shared back to a central server. This approach ensures that raw data remains private while still enabling collaborative model training. It's particularly impactful in fields like healthcare and finance, where privacy concerns are paramount. What a day! This concludes our day 1. Thanks for watching. For more technical courses and interview materials, please go to our website at bowsea8.com.